Well, hello again. I am back to teach you more about exponential functions. And what you have here is we're taking an exponential function that we've graphed before, but we're adding 1 to the whole thing. So what does that do to the graph? How can we affect the shape of the graph? Well, let me show you. We've looked at the standard exponential graph, just the basic a to the bx. But what if we change that x value and that y value? So now over here, what I've got is I'm going to show you this graph. Now, the h and the k value are both set to 0. So the purple graph and the orange graph are exactly the same graph. What happens when I change the h value? Remember, the h value is affecting the x value. Now, it might look like it's flattening out, or what it's really doing is just moving left and right. That is all that it is. It's moving left and right. And of course, the k value, which affects the y, is going to move it up and down. So let's say we have a graph. Let's say the graph right now. See how it levels out at 0? We talked about that. It's never going to reach 0. It's going to get really, really close to 0. What happens if I move the whole thing down 1? Is it going to go past -1? It never, ever, ever, ever will go below -1. So think about that in terms of range. The range, which is the y value, will never go less than -1. Wherever I put this value, now I put it at 5, it will never go below 5, ever. All right? Now this h value, I'm going to move it left and right. Does that actually change the domain? No, it's always going to be anything. You can put any number you want in for x. It's just going to move it left and right. So if I take this graph and I moved it 3 to the left, moved it down 1, you see how it compares to the original graph. It's the same exact shape, but it's moved down 2 units and moved to the, what's that direction? To the right 3 units. That's how those values change your exponential function. So now let's graph a couple of those. All right, now that you've seen that, let's put this together. So let's start at 0 again. All right, so it's 1.5 times 2 to the 0 plus 1. Okay, 2 to the 0 is 1. 1 times 1.5 is 1.5. So we're starting at 1.5. Remember how I said before, that's not your y-intercept that you want it to be. But it's not always that easy. That 1.5, we're going to add 1 to it. So we're going to end up with 2.5. Now, the scale factor is 2. That doesn't mean we're doubling 2.5. The next one is not 5. What are we actually doubling? We're doubling the 1.5. 2 to the first is 2, and 2 times 1.5 is 3, and 3 plus 1 is 4. So you see that? We're not actually, in fact, let me do this. Just, sometimes it's better to have too much work than not enough, right? And this one we said was 3. So notice, these are the ones being doubled, not the ones. The one just tacked on at the end. So let's do it again. We're going to multiply by another 2. So this 3 will be 6. So you see the little pattern? If we double it again, that'll be 12, which leaves me a day after my birthday. Oh well. All right, can we graph that? 0, 2.5, probably a little higher. 1 is 4, 1, 2, 3, 4. 2 is 7, 4, 5, 6, 7. And it shoots up that way forever. We can't fit the 3. Now, here is what happens. You must be careful. What does that plus 1 do? Remember, usually it levels out at 0. But if we have a plus 1, it levels out at +1. It levels out at 1. That's the change. It all shifts up 1. So our domain is still all real numbers. It's everything. Our range, however, is now y is greater than 1. That whole thing shifts it up 1. Okay, that's the difference. Now this -2 is happening just to the x. So what does changing the x value do? Remember on the video? It just moves it left and right. So, again, let's look at a table and see how that works. Now I usually pick 0, but I'm not picking 0 this time. I pick 0 because I like taking things to the 0 power. Well, if I let it equal 2, x equal 2, I get 2 minus 2. And of course, 2 minus 2 is 0. And 0, the power of 0 is 1. 0.5 to 0 is 1. 1 times 3 is 3. So let me move up. If I go up in x, now I've got 3 minus 2. 3 minus 2 is 1. 1 times, or 0.5 to the first power is 0.5. So what's half of 3? You think of it as 1.5. So it looks like my scale factor of 0.5 means that every time I raise this by 1, so it's squared, so it's 0.25, so I'm doing another half of this. And I can be taking half of that forever. So let's see, how will this fit on the graph? What if I did 1, 2, 3? How would that look? So when I go out to 2, I go up to 3. 1, 2, 3. Oh, it's right here. Wow. When I go out to 3, I go to 1.5. So that's 1.5. And when I go to 4, I get 0.75. Well, that's dipping pretty quick. So there's 1. There's that. So it's right about here. So the graph's going to look like this. It's going to flatten out. It's going to go up forever. Now it's still going to flatten out at 0 because we're not affecting the up and down part of the graph. We're only affecting the left and right. But think about it. If I take infinity and slide it over, it's still infinity. But if I take something that stops at 0 and slide it up, then it stops somewhere else. So the range is everything greater than 0. Okay? Now, if anybody's curious as to where it crosses the y-axis, you just have to plug in 0 for x and figure it out. I'll let you do that because we're going to handle that later anyway. All right. We're subtracting 8. So before I go any further, what does subtracting 8 mean? It means you move it all down 8. Now my scale won't let me move it down 8. 1, 2, 3, 4. So you tell you what, let's do a scale factor of 2. We'll make that -8 right there. Okay. Now let's do a fun little table and see if we can see the trend of this graph. Now if you got your graphing calculators at home, you can plug it into your calculator, look at a table, and see how that works too. But I want to do it by hand just to get you to feel the realness of it. So let x equal 0. All right, anything to the 0 power is 1. That's a bad 0. Let's try that one again. Anything to the 0 power is 1. 5 times 1 is 5. 5 minus 8 is -3. Now my scale factor is a half. That means every time I'm going to take this number and take half of it. So what's half of 5? 2.5. And what's 2.5 minus 8? -5.5. Now I'm going to take half of this again. Remember, not half of the whole thing, half of this number here. So let's see. So that was 5. Then it was 2.5. What's half of 2.5? 1.25. What's 1.25 minus 8? It's 6.75. So that's probably enough to get a decent looking graph here and see what we got. So let's graph 0, negative 3. This would be 2, be right here. 1, negative 5.5. 4, 5, right about there. In fact, let me take this and move it. Whoops, that's connected. Won't be able to. Let me put this out of the way and put the negative 4 over here. Okay. I'll try that point again. So 2, 4, 5 and a half. It's an approximation, and 2 is negative 6.75. 2, 4, 6, just before 7. So it would kind of bend like that and then go up. All right, it doesn't actually dip back, but you know that's the limitations of my pen. So the domain is everything. And the range, how is the range affected? Well, that shifted it down 8, so y has to be bigger than negative 8. All right. One more graph, then we'll apply it to some problems here. So I got a lot going on here. So it's all wrong. Damn it. Okay, I got a lot going on here. I'm starting with a half, I'm tripling it every time. I'm adding 4 to the x, I'm shifting it over 4, and I'm moving it down 5. Oof. Lots. So let's do down 5 first. 1, 2, 3, 4, 5. So let's call that 5. Okay. Now, let's make a table. Let's see what's happening. Oh, I don't want to start at 0. I want my exponent to be 0. So what can I add to 4 to get 0? Negative 4. Again, you don't have to do it with these numbers. I just like to do it with these numbers. So negative 4 plus 4 is 0. So 3 to the 0 is 1. 1 times a half is a half. So a half minus 5 is negative 4.5. Now we're going to move it up by 1. If I move it up by 1, this is going to be a negative 3 plus 4, which is 1. So I'm going to be tripling a half. A half times 3, which is 1.5. Now if I subtract 5 from 1.5, I would get negative 3.5. All right, and I'm going to keep on going. I'm going to multiply it by 3 again. So 1.5 times 3 is 4.5, is negative 0.5. And I don't think I can fit anymore, but we'll try it. So I'm going to multiply by 3 one more time. Oh yeah, 4.5 times 3 would be, what, if you make it double, you add 4, I get 9. 13.5 minus 5 is 8.5. I do not believe that will fit on the graph. Let's see what we got. Negative 4 is negative 4.5. 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4 and a half. Negative 3 is negative 3.5. 1, 2, 3, 1, 2, 3 and a half. Negative 2 is 0.5. Negative 2 is 0.5. Is it 8.5 doesn't fit. So it's going to shoot off forever, and it's going to come down and flatten out and not go less than negative 5. So domain is everything. And the range, y has to be bigger than negative 5. Okay. Separate those a little bit. All right, those are graphs. It's almost every kind of graph you'll have an exponential function. But the cool thing about them is how to use them in application problems. So write an exponential function. Now there's 2 things we have to know. We're starting with 12,000 initially, and it doubles each day. So what does that mean? That means that's the A value. And the B value is double, which means 2. That's your B value. So your equation is actually going to be 12,000 times 2 to the x. We're doubling it every day. So the question is, after 6 days, how much are you going to have? Well, you put that in a calculator, you're going to get 768,000 bacteria. And I just realized that's kind of my birth year. It's all here. Look at this. July 12th, 1968. Crazy, huh? Okay. Now, did you need to know exponential functions to be able to do this problem? No. You could have figured out this problem doing it this way. Whoa, that's not where it goes. That goes over here. Initially. So we call it day 0. There was a movie, I think, one time called The Zero Patient. It was about a virus. And the 0 patient was the first one that had it. Not the first person. So he wasn't patient 1. He was patient 0 because he was the start. Anyway, one day you double it. 2 days you double it again. 3 days you double it again. 4 days you double it again. 5 days you double it again. So guess what? On the 6th day, you've got that. So you didn't need a whole lot of high mathematics to do it, did you? But imagine if I asked you what it would be like on the 100th day. Oh, you don't want to do that 100 times. So you just plug 100 into that formula. Boom, there's your answer. All right, thanks for bearing with me. One more. 4,000 students. 5% growth rate. What's the formula? So you might be thinking, all right, cool. We're starting with 4,000. I got my 5%, which I know is 0.05. I'm going to use t for time this time instead of x. But if you plug in 5, what are you going to get? All right, let's figure that out. 4,000 times 0.05 to the 5th power. I get this. All right, we got ourselves an issue right there. How in the world could that number have gone down? Well, if you think about it, the number that we chose here is less than 1, so it should go down a lot. It's like I took 0.5 of it every time. Well, that's not going to help me figure this out. So there's a little trick that we need to do. We got to put a 1 there, because that 1 means the 4,000 you started with, and that 0.05 means how much it's going to go up by. So we have a little formula that I'm going to share with you. You're going to notice it looks just like AB to the x, except it's not b, it's this thing. So if you ever have a percentage or a rate, if you add 1 to it, you get the right answer. And now if it's a decay, if it's going down, it's 1 minus r. So just remember this formula when you do these problems that have percentages. Now let's see what answer we get if we plug that in. So 4,000 times 1.05 raised to the 5th power. That's a little bit more like it. Now it's a decimal, 0.12625, but we're not going to worry about that. We're just going to say there's about 5,105 graduates in 2025, because that's 5 years later. So that's the basics of that's the basics of exponential growth and decay. So try those problems. I only gave you like 8 to do, just to get the idea of it. Okay, and I'll have a live session on Tuesday, and I can go over any of these questions that you like. These are due on Tuesday evening, and we're going to go from there. So have a great one. Bye.